Hey everybody, this is Austin with austins.nerdythings.com. Today we'll be talking about how to obtain millisecond accurate NTP using Crony and a USB GPS, a $12 USB GPS. So I will basically be following along the blog post on this, which the address is right here. I will post that link in the description. This was pretty popular on Reddit in certain groups. So I decided to do a YouTube video on it. This is running I'm running this on an Ubuntu virtual machine using VirtualBox. I passed through the USB GPS to said virtual machine. It's just easier to record that way and not have to deal with multiple devices because I'm sitting at a park near my house because I don't want to have to blur out all the coordinates that will be popping up throughout this video. So, that said, I do have the USB GPS sitting on my dash. I will take a picture of it and put it in the video. It blinks once per second when the device has a lock, and it definitely has that. This is a very sensitive GPS, so I'm using the GT-U7, which is $12. The link to it is right here. So I had some technical difficulties in the earlier iteration of this video, so I basically just restarted and started recording again. So I have already done a couple of these steps. For any of these projects, first thing you want to do is update your package manager, which you can do with sudo apt update. Upgrades everything to the latest version. I originally wrote this for a Raspberry Pi, so you can do a Raspberry RPi update. But the most important packages to install are the ones right here. So I'm going to hit paste, and then you will see. So this is in Ubuntu. It doesn't actually have the Python-GPS packages. So we would just install these guys instead, which is GPSD clients, and Crony. And we can see that these are already the newest versions because I already installed them. So next up, what we have to do is modify the default GPSD settings, which we can find. Let's see here. Sudo nano /etc/default/GPSD. So I already have these pasted in here. Start daemon equals true. Means it automatically starts at boot time. USB auto means new USB GPS devices will automatically be added. The device is what it's referred to. For Ubuntu, Raspberry Pi, a couple other probably Debian-based distributions will use TTY ACM0. It could be /dev/TTY USB0. And then -N means we're going to start listening to GPS data without a specific listener. So I already have that done, and what I did not do last time I tried recording this video is I did not reboot. Reboot to make those changes take effect. So that's where we're at now. After the reboot, we're going to start editing the Crony configuration. Let's see, Crony. And so the important line here is ref clock, which means we're going to add a reference clock, SHM, shared host memory. 0 is the reference for that. ref ID. We're going to call it NMEA. Offset is currently 0.000 because we do not know what it needs to be. We will be setting this. Precision 1e-3 is 1/1000th of a second. So this is saying we have millisecond precision here. Pull 3 means pull every 8 seconds. It's 2 to the whatever number. No select means don't use this. This is important because, as I mentioned, we're going to be measuring the offset. So I also have NTP pool here. To get a time, because as I said, we are sitting in a park. I do have more accurate time sources at home that I use to set this. Namely, this device here is a PPS reference. It's very accurate. Okay, so once this is done, restart with sudo system control restart Crony. And then, so that was 3A. 3B is if you want to use NTP. Which you are free to do. It's basically the same things here. Min pull 4, max pull 4 is pull every 16 seconds, which is what you want for NTP. Still have the no select, still have the offset. Stratum 2 means it's not a super accurate source, and we're just going to call it GPS instead of NMEA for that. You can call it whatever you want. Okay, so to get the rough offset, what we're going to do is GPS mon, and so this is GPS monitor. So the important line here is this T off, and it looks like it just stabilized at a value I would expect. GPS mon is, monitor the GPS data coming in. Up here in the upper left, you have satellite information. This middle big box is position, velocity, solution type stuff. So we have 8 satellites being tracked, 9 satellites being tracked. And what we're interested in is this T off, which is time offset. So it's 0.062. That's like 62 milliseconds off of what the system time thinks it actually is. So I'd go to 0.7070 there. That's 70 milliseconds off. This GPS mon looks a little bit different because it's Ubuntu. The screenshot and the blog post is from a Raspberry Pi. So in this instance, the T off was 0.81. It'll be over here if you have an older version of GPS mon. One note about the timing, Windows itself is not great for timing, and then having a virtual machine inside of Windows means it's even rougher for timing. So I do not expect really any good results here. You want to be running this on Linux, ideally on a bare metal Linux instance. If you're running in a virtual machine with a Linux host, that will kind of work. But really you want the bare metals to have, skip all the clock virtualization type stuff. Okay, so we're going to, this T off, you could set it at whatever value you get here, 0.060, but that's not going to be super accurate. So what we're going to do is instead get a data-driven approach for this. So we are going to modify the Crony configuration file and uncomment this line to turn logging on. And then we're going to restart Crony. Alright, and so this will output 3 different kinds of files, measurements, statistics, and tracking. They have different information in them. So the one that we are interested in is the statistics.log. So before we do that, let's check out what sources Crony is using Crony C sources. So we can see here that the asterisk is what is currently being used, alflin.canonical.com. So it's saying we're 13 milliseconds off of that. Like I said, if we're using my phone as a hotspot right now with highly variable latency, this is a Linux virtual machine in a Windows host. If you do these steps on the bare metal Linux with a decent internet connection that has stable latency, minimal jitter, you will have great results. So we are collecting data. Our NMEA source is 62 milliseconds behind of what time the computer is actually using, and this will change every so often. We can actually do watch -n1, so every second run this command again, Crony C sources, and a lot of this stuff only updates every so often. So these 4 canonical sources are only updating every 64 seconds, which is 2 to the 6th. Our GPS device should be updating every 8 seconds, so it's somewhere in that range, 58, 60-ish, whatever. So what we're going to do is, now this has been collecting data for a bit, we're going to look at the statistics, and we're going to use grep to pull out the NMEA lines, and I'm going to make this bigger. And so here we have some offset data. The next line down will include the header information as well. So let's pull that guy out. Okay, so here's that same data with some header information. The column of interest is this estimated offset. It's basically the second column of actual data. And so this is kind of all over the place. I had much better results at my home internet connection, and actually the better place to look is probably in this screenshot. Estimated offset, you can see these are fairly stable around 7.8 E-2, which would be 0.078 or around that. So column of interest is the one after the 9014 column. Let's see what it is in here. Doesn't have it. Oh, that was for NTP. Okay, so anyways, what you want to do here is, copy and paste this information into Excel and get an average. We're just going to eyeball it. We're going to call it, like 0.558, 0.058. And so that is the number that you would put into the offset. And so I actually already have this figure for this exact GPS with much better time stability. So I said 0.58. That's what the eyeballing, that's what eyeballing this column would be. But we're actually just going to use 0.0763 because I have previously measured this. So what we do with that is go ahead and edit this reference clock line. And we'll be putting 0.763. So that means that this clock, the synchronization information comes 76.3 milliseconds, after the top of the second. So this basically adjusts the clock forward by that amount. So Control O, Control X to write, restart Crony, and then we will watch it and see if it selects our source. And so yeah, I have here watch Crony sources or NTPQ-PN to see if the USB GPS gets selected. So far it has not. We're still using alphin.canonical.com. Canonical? I don't know if I've ever actually said that word before. And so in this screenshot here, you can see that on the Raspberry Pi, it did select the GPS NMEA source as the source to use. I did not get it to use the GPS source last night at all with this virtualized Ubuntu on a Windows host. There's probably also some delays in passing through the USB. But if you follow these steps on a bare metal, you will get a Linux system to use your GPS. I had this plugged into a pfSense appliance, and it's pretty consistently within 1.5 milliseconds with a jitter of about also 1.5 milliseconds, which is plenty accurate for home use. Alright, so for Crony, you would see something like this, and this text in the above screenshot, we can see that Crony actually has the NMEA source selected as the primary source, denoted with the asterisk in front, and it has the Raspberry Pi PPS NTP GPS ready for takeover, which is Pi NTP. At my house, that is the most accurate time source. It's very accurate. So what we've got over here is this alphin.canonical.com. Is the main source. It's ready to take over as Golem, and it's still unsure about our NMEA and Chili Pepper, and it says we're not going to use pugo.canonical.com. These are what the different symbols mean. Question mark means it doesn't know yet. Minus means not going to use. Asterisk means using. Plus means ready to take over as the backup. It's basically the second best source. So what I've got here is for some discussion, is plus or minus 5 milliseconds good enough? And I say for 99% of use cases, yes. You can stop here and your home network will be plenty accurate. If you want additional accuracy, you are in luck. This GPS module does output a PPS pulse per second signal, which I have used on another Raspberry Pi to get within very close 0.05 milliseconds or 0.0005 seconds from the official atomic clock times. Basically, all the GPS satellites have atomic clocks in them, and that's how they keep very accurate time, and we are just one step away from that. Alright, so in conclusion, we got this u-blox USB GPS set up and added as a reference clock to Crony. And if we weren't all sorts of virtualized, we would be within 10 milliseconds of official GPS time. I said you could write a script to do all this for yourself. Maybe if you guys are lucky, by the time you watch this video, there will be a script posted. So the next post, which I have not wrote yet, we can add pulse per second signals for the GPS module to increase the time accuracy by factor of 1,000. So that's getting really accurate, entirely unnecessary for basically any use case. But if you're kind of nerdy about time or otherwise like nerdy things like I do, and why I named my blog Austin's Nerdy Things, then you are in luck. So I do have some other notes on why having the faster message transmission time. With standard GPSs at 9600 baud, it takes 69 milliseconds to transfer a sentence. And so if you actually use the U-blocks with its binary messages, they seem to always be 60 bytes, and at a much faster transmission speed, it takes 8.33 milliseconds to transmit the sentence and the message. So that's a lot better timing. The less jitter, the more consistent the timing of this thing, the better the results will be. And here's some more discussion on that. So in an ideal world for timekeeping, GPSD would automatically disable every sentence except for time and bump up the baud rate to the highest supported level. But unfortunately for us, GPSD's default behavior is to just work, which basically means don't configure the GPS. And GPSD works with 99.99% of GPSs out there. So well, we still haven't locked on. Like I said, I'm not surprised that hasn't happened. You do this anywhere else, or you can see in the blog post that it locked on. It even preferred it over my PPS source down here, which was kind of amazing to me. But you'll have decent luck. So that is that's the full video. If you like this video, go ahead and click like. If you want to see more things like this and be notified when I release other videos, also click that subscribe button. Next up will be the PPS video. And actually, let me just bring that up real quick. So this is the microsecond accurate using a GPS wired in. So you can see this PPS pin here. GPS model we just talked about has one of these, but I have not soldered the pins up yet. So same kind of stuff. Here's some wiring information. Here's a picture of the GPS antenna in my basement. It still has 9 to 11 satellites all the time. Testing the PPS source. And then here we can see this PPS. This is really close to the actual time. So let's see what we have here. We were 289 nanoseconds off of actual time. So that's pretty good. You're not really going to get better than that at home. But anyways, enough about timekeeping for now. Like I said, click like and subscribe if you like these kinds of videos and want to learn more nerdy things. And we will see you guys next time. Thank you.